Good afternoon, everyone. I'd like to welcome you to this very special union session that we're having today, titled Climate Dynamics, Theory, Modeling, and Breakthroughs. And the motivation for this is the 100th birthday of Jule Charney, one of the pioneers in many areas of climate research and associated fields. Today we have three very special speakers, all of whom were students of Charney at MIT, and you can see those listed here. I'm going to be handing the podium over to Natalie Burles, who will be doing the introductions of our speakers. And then after the first hour, we are going to invite them and some other members up for a little panel discussion section, which Jay Shukla will be emceeing, I guess would be the right word. So thank you again for attending, and now we shall start.
Great, so welcome everyone. I'd like to introduce our first speaker for today, Kerry Emanuel, and his title of his talk is going to be Would Jule Charney Have Cracked the Madden-Julian Oscillation, which I think is a really intriguing title, so I look forward to hearing your talk.
Well, thank you very much. It's a pleasure and honor to be with you here today. I have a confession to make. I really just put Madden-Julian oscillation up there to try to draw as many people into the room as I could. And I know it's always a big job because half of the field works on this problem. That's it, okay. What I really want to do is talk about Jule Charney, and who was my advisor and my friend. I was very privileged to know in the last 5 years of his life. And let's see, here we are. Oh, it's the left-hand button, just for the other people. Jule was not only an amazing scientist, and I'm sure that will come across, if not in my presentation, in the collection of presentations, but he's also an amazing person. I think it's fair to say that of all the scientists I've met in my lifetime, hands down, Jule was the most charming. He was a charming man. He was fun to talk to, he was fun to be with, and he was a great scientist. One of the characteristics of his science that I most admire is in the fine tradition of physics and mathematics. He simplified things. He was a great simplifier. And I'm going to start by putting up a short list of his accomplishments. You'll hear more about that as we go on this afternoon. The first thing he did as part of his PhD thesis was to develop the first real linear theory of instability, of baroclinic instability. Edie did it at about the same time, although published later. And it was a beautiful simplification of what had been regarded as an enormously complicated problem at that point. He developed the set of quasi-geostrophic equations, which everybody here who's been in dynamical meteorology or oceanography will be familiar with, that allowed us to conceptualize in a way that was, before that, very, very difficult, atmospheric and oceanic dynamics. He developed the necessary conditions for baroclinic, barotropic instability, which he did with Philip Drazen. He was instrumental in producing the very first numerical weather forecast. He developed a nonlinear theory for western boundary currents in the ocean. You'll hear more in a little while from Mark Kane about his contributions to oceanography. Developed with Stern the theory, sorry, I've got Stern and Drazen mixed up now, with Drazen, a theory of upward propagation of waves into the stratosphere. Developed the theory of quasi-geostrophic turbulence, advanced nonlinear theory of blocking later in his career. And besides his strict research accomplishments, he also contributed greatly to many important projects. The Global Atmospheric Research Project, he was very important contributor to the organization of that. And he headed the first National Academy of Sciences report on anthropogenic climate change. What a stellar list of accomplishments, and this is only a partial list. So to get back to one of the early accomplishments, for many, many decades after the Norwegians had sort of developed a conceptual model for baroclinic cyclones, and came up with this picture, the modern depiction of this picture of the Norwegian schools illustration of the stages of the life cycle of a wave cyclone. There are all kinds of attempts to understand this theoretically, but what Jule did was to bring to fluid dynamics, to this aspect of fluid dynamics, ideas that the physics community had applied, or other aspects such as the aeronautics community had applied to understanding fluid instabilities. And really boiled the whole thing down to one relatively simple ordinary differential equation in a kind of perturbation pressure that you see there. No need for me to go through and describe the terms, but this is basically what Jule boiled the problem, the linear problem of baroclinic instability, down to. And quasi-geostrophic theory is one of his most beautiful accomplishments, and one of the most beautiful accomplishments, I would say, in our entire discipline. And he stated very succinctly what others have later put into slightly different words, that the motion of large-scale atmospheric disturbances, and I think we could add oceanic, and some oceanic disturbances as well, is governed by the laws of conservation of potential temperature and absolute potential vorticity, and by the conditions that the horizontal velocity be quasi-geostrophic and the pressure quasi-hydrostatic. And that sort of got put later on into the terms of invertibility and conservation of potential vorticity, with boundary conditions of potential temperature. So let me ask this kind of quirky question. One of the great problems, which I'd argue is essentially been solved fairly recently, some will disagree with that, but which took decades to solve, was the problem of the Madden-Julian oscillation, the MJO. Now, Jule must have known about this, but it hadn't been discovered very long before he passed away. I don't know whether he ever worked on this problem. I don't think so. There's no publication record that suggests it. How would he have approached this, given how he approached other problems? Well, this dates back to the famous paper by Madden and Julian in 1972 that shows the power spectra of zonal winds at various levels from a radiosonde near the equator in the tropical Western Pacific, showing a distinct spectral peak in the region of 30 to 60-day periods, which has become since known as the Madden-Julian oscillation, or MJO. The people who have quantified this observationally have done an absolutely beautiful job of it. This is a result using MSU satellite data together with, I think, reanalysis winds, showing the relationship between winds, temperature, and outgoing long-wave radiation at the top of the atmosphere, and with 1,000 millibar winds in the bottom panel. So we sort of have known for a while what the structure of this was. And when we look, we decompose the satellite measurements of outgoing long-wave radiation into a power spectra and a wave number frequency domain. This is from the very nice work by Wheeler and Kalidas almost 20 years ago now. It happens that the peaks, after you've sort of filtered the red background spectrum, lie along those black lines, which are dispersion curves for the just the linear normal modes of the equatorial beta plane shallow water equations. And so that's a very intriguing thing, that something that looks that you've gotten directly from observation seems to line up with something that's from a very elegant, simple theory. I think Jule would have loved that if he had been around to see that decomposition. So now I'm going to make some provocative statements here. Some of the best minds in atmospheric science threw the full weight of dynamical approaches at the MJO problem over a period of decades, and I'm among the guilty, so I think I feel a little bit better about stating it this way. Leading to increasingly complex ideas. And I'm going to put one up. I'm going to quote from a paper, and I'm obviously not going to tell you who the guilty party is, but there are lots of guilty parties, so it doesn't really matter. So here we develop a multi-scale model that focuses on planetary scale circulation anomalies induced by interaction with equatorial synoptic scale circulations created by a wave train of superclusters. This is an analog for the tropics of the mid-latitude baroclinic instability problem, which I don't think it is, by the way, where the superclusters are the equatorial synoptic scale disturbances, and the MJO is predicted as a planetary scale response through upscale transfer of kinetic and potential energy. Now that phrase is interesting because it encapsulates a lot of concepts that Jule Charney actually developed, like the upscale cascade of energy and quasi-geostrophic turbulence. But on the other hand, the whole construction of the sentence and the whole approach to science, I think, is almost antithetical to what Jule was doing, which was to try to simplify things very greatly. And one of the problems is that if you put this in the long context of the development of atmospheric sciences, going back to the 19th century, most of the weight very shortly after the discovery of the first law of thermodynamics was on purely thermodynamic explanations for phenomena like the thermal theory of cyclones. The Norwegians, if you read their papers, balanced dynamics and thermodynamics, but after Charney and Eadie, we went into a dynamic-centric world. And I've just illustrated this with a factoid here. In AMS journals, and I think this is in the last 10 or 15 years, I've forgotten the time period, there are 1,452 titles with the word dynamics and a mere 265 with thermodynamics, but that's changing now. So we're going to now switch to a concept which came from, almost arose by accident, one might argue, that was discovered in work that had nothing to do with, at least initially, with the Madden-Julian oscillation. And that came from looking at experiments of radiative convective equilibrium in just simple boxes where radiation was calculated and convection was explicitly, albeit crudely, simulated. And phenomena like this, clustered convection, in these simulations began to emerge spontaneously. So here, for example, as a snapshot in a simulation in one of these doubly periodic boxes showing the outgoing long-wave radiation in the sort of state of classical radiative convective equilibrium where the convection is pretty much random in space and time. That's how we all envisioned RCE to look like. And indeed, in the early simulations, and simulations in early times, it does look like that. But then there's this dramatic change in the sort of phase space of the problem. And after a while, under some conditions, the convection collapses to a single cluster, as you see here, and pretty much remains that way. And this is, I think, one of the most important discoveries of the last 20 years. This was a discovery made, it has to be said, in a complex numerical simulation. That it poses a challenge to all of us. What's going on here? And is there some simple way of explaining this? Could have very profound effects on climate. Well, since that time, we've seen this happen in a variety of different frameworks. So here's from a paper just 2 years ago by Nathan Arnold and David Randall, who looked at the SP cam, so it's cam with kind of a superparameterized convection. And it just shows a sequence in time, day 10, 15, and all the way out to 120 on the right, of the column integrated water vapor. And you can see by the end of the simulation these gigantic clusters. This is on a planet which is rotating at the speed of the Earth, but is an aqua planet with constant SST everywhere. And they were able to show that if you homogenize the radiation, this went away. So if you look at the top row, the simulation I just showed you is at the upper left. If you homogenize the long wave radiation, it doesn't form those clusters. And it was known from the very beginning of these studies that if you don't allow for the interaction of radiation and clouds and water vapors, this doesn't work. So this is a thermodynamically driven mode of the system. I won't go on to the other simulations. This has since been repeated in simulations where the convection is explicit everywhere. This is from a work that I'm doing with Murat Karatnadov, showing a kind of broad equatorial channel in RCE with constant SST. You can even see some tropical cyclones at high latitudes there. And that does produce a very nice Madden-Julian oscillation type of mode in the wave number frequency space you see in the lower left, together with some of the other modes we observe. And again, if we do some compositing of the MJO around its OLR maximum, the yellow dot, This is the correlation of the OLR with the radiative transfer. And you can see that by looking at the upper two panels, the disturbance is amplified by radiation, but in this case it's propagating eastward because of the effect of surface fluxes. So there is no MJO with horizontally homogenized surface fluxes and radiation. That's very important. And I would argue that very recently, Tom Buechler and Tim Cronin boiled down. This is the part I think Jule would have absolutely loved, even if he hadn't done it himself. They boiled the criterion for the aggregation of convection down to a very simple criterion, which is the rate of change of radiative heating with column integrated water vapor has to be larger than 0. So if you moisten a column and it results in net heating, this instability will erupt. And that part is very like what Charney would have done. So whether he would have done that or not, anyone can guess. But I have no doubt that he would have admired that result greatly because it's simple. And I'm going to skip that because I'm running out of time. Jule clearly had a knack for boiling things down, boiling problems down to their very essence. His work fostered a really amazing era of rapid progress in dynamical meteorology. And had he lived longer, he might have recognized that important unsolved problems would require conceptual understanding of clouds and radiation. And I'll leave you with that picture that was taken way back in 1980 up in Maine of myself and Jule. Thank you very much.
Thanks very much. So we have time for one or two quick questions. Unfortunately, we're still waiting on the microphones for the audience. So if you'd like to ask the question, we'll do our best to repeat it for everyone else.
Could you show the slide you skipped?
I'll try. Oh, this one? Yeah. Yes, that's a cartoon from the Buechler and Cronin paper. Basically showing that if you start with radiative convective equilibrium and you introduce a perturbation, a moisture perturbation, and it results in, well, their Q dot was the negative of mine. They called that radiative cooling. If the radiative cooling decreases, you'll get more upward motion in a moister atmosphere, and that's their sort of conceptual cartoon of the instability. So all that multi-scale stuff and all that really complicated dynamics is being replaced by a beautifully simple largely thermodynamic explanation. And that's what I think Jule would have loved.
Great. All right. Well, thanks very much. We'll divert any other questions to the panel discussion later. And so now we can introduce our next speaker. So our next speaker is Inez Fung. And I'm just going to quickly switch across to the...
Thank you. When I was a graduate student, I learned Fortran, and I went to Charney, and he says I had to solve my thesis analytically because I would be doing modeling for the rest of my career. So I think that's very important to me. And then when I was a postdoc at Goddard Space Flight Center, that was before the term two-body problem was coined, and I was commuting between Washington and New York, and Charney came to Washington and said, your work is only part of your life and do not confuse the two. So go back to New York. And that was after the first NAS report on climate. And I said, what do I do? Nobody knows Navier-Stokes. So he said, learn the carbon problem. And so I started all over again, and I wrote notes for him. He said we would do something together, and I wrote notes because he always asked questions I could not answer. So I wrote elaborate notes for him. Unfortunately, he never saw them. So here I am talking about carbon, something that Charney totally changed the direction of my career from Navier-Stokes to chemistry and biology. So I think the Paris Agreement you're all familiar with, that prior to 2015 is the emission trajectory that we've been on, and after 2015 is what we need to do. What we need to do to achieve 2-degree warming. Emphasis is that we're not slowing down, but the reduction in the emission. And what the countries, the 4 top emitters, have pledged is already exceeded that. So what we do when I'm thinking about fossil fuel emission, the way we estimate it is by knowing the fuel rate and then multiply by emission factor, which is a lookup table, or we measure the activity and then we multiply by emission factor, which we look up in a lookup table. So the emphasis here is that emissions from fossil fuel combustion are estimated and self-reported. The UN statistics is self-reported by different countries. In California, cap and trade is also, please fill in this spreadsheet. So what we need to do is trust but verify. Voluntary compliance is not that effective, and what we need is some instrument or some capability to actually monitor what the compliance levels are. So for CO2 and for national emissions, the challenges are many. Our contemporary network, you all know the familiar and Mauna Loa and South Pole stations and other stations, they're located at remote marine locations because over land you have large CO2, as the land, the daily photosynthesis and decomposition gives very large oscillations, which we would call noise in the olden days. Okay, so then to infer the CO2, the sources over land from remote marine locations is very difficult because there's atmospheric transport. So to verify the emissions, what we have done is to develop a carbon weather data simulation. As I said before, emission verification, there's no such thing as verification because the commitments are voluntary. So what we're hoping to do is to develop the system that we could share with other research groups around the world so that we can encourage emission reduction. There's no such thing, there's there's no fine if you exceed the speed limit, okay? So here what we've done in collaboration with Eugenia Charney, and many of you know Eugenia Charney from NCEP reanalysis. Eugenia was Charney's student and the first woman PhD from the MIT department. So what we've done is to do data assimilation, many of you know, is to combine information from imperfect model, incomplete observations to give the best estimate of the meteorological state and CO2, and then from there infer the surface sources and sinks in the same way you use NCEP reanalysis to get evaporation at the surface, for example. So this obviously started with Charney. His paper with Milt Halem, who's sitting here in the audience, 1979 paper, didn't use the word data assimilation. It says use of incomplete historical data to infer the present state of the atmosphere. And so at the conclusion, so basically using temperature, prior to that, the initial conditions were obtained by statistical interpolation and extrapolation. So here is using the laws of physics here, the fluid and very simple at the time, the simplified version of the Navier-Stokes equation, and use the temperature, the trade-off of temperature for wind. So you can immediately see the geostrophic balance and other terms there. And so so the NCEP reanalysis, so this is the very familiar now to everyone, growth of data assimilation And this is not the only group, obviously, there are many other groups. So for that, we now have 40 plus years of 6 hourly wind, horizontal wind components, temperature, specific humidity, and temperature. And higher resolution products are now available from other centers. So what we're doing here is to say the data assimilation. So we use the model, and we're running 20 ensembles. Then we make a forecast in 6-hour forecast. Then we bring in the observations, and then we do an optimization of the model, the incomplete model, and then we go forward and make the forecast. So what we're doing here is the imperfect model is Chem5, which has the carbon component in it, the NCAR model, and the incomplete observations are the meteorological observations and the satellite CO2 observation, and then the optimization algorithm is the Kalman filter from Jeff Anderson's group at NCAR from the data assimilation research testbed. And so then we produce the 4D CO2 fields and then infer the, wrong way, sorry. So here is an example of the weather. So weather observations, and this has cloud. This is not the complete list. I'm just showing you. It's just incomplete observations. They're not synchronous. They come at different times of day or night, and so you can see the color bars, just the number of observations. So many of you do this with data assimilation. So basically, we're using the equations in the model to extrapolate and interpolate among all these. And then the CO2 observation with OCO2, the Orbiting Carbon Observatory 2. And so this is an example of the polar orbit. So this is on the NASA A train. The equatorial overpass time is about 1:30 in the afternoon. So each pixel is about 3 square kilometers. So it's very exciting to see the column, to be able to observe the column CO2 from space. So what we're doing, so what I want to just very briefly talk about is an experiment, and I suppose, okay, this is suppose, it's not for real, okay? Suppose the reported emissions from China are underestimated. I have many reasons for questioning that, because there are many papers that question the emission factors that are used by IPCC and other sources. So they knew different kinds of coal, different kinds of emission, etc. So there's questions about the statistics. So the question I'm asking is, suppose that a country has underestimated its emission, can we tell using satellite observations? And so I'm going to talk about a 2-week experiment in October 2014. And so the first thing is that because I'm running 20 ensemble members with the weather, okay, so we have the uncertainty in here. I only show the uncertainty in the surface pressure. Eugenia County always told me that we predict, in weather forecasts, we predict the uncertainty, we predict the error in the forecast, okay? So this is where we have 20 ensemble members, and where we have high uncertainty when the spread is large, typically where there are storms, and you can see very clearly the storm tracks, where there's convection is uncertain. And so when that goes, so I'm going to focus on East Asia, where we reduce the emission, and also over the Gulf Stream region. So when we look at the results, the innovation, which is the extra CO2, because I reduce the emission in this experiment, then to match the observations, then we see in the 2 regions, surely over East China, where we had where it's underestimation, we can recover the underestimation. But over the Gulf Stream region, where we didn't do anything, we are actually required more emission from the Gulf Stream region. So one could go through, so that's not good news over the Gulf Stream. So what would go in and understand, and I emphasize that I don't want to give you, say, oh, we can do everything. No, this is a learning exercise. So what we can see is that the innovation, the spread in the innovation over the Asian region, you can see is related to just local convection, okay, whereas the spread over the Gulf Stream region is related to the excess advection by the storms. So the storms were too strong, advected the CO2 away, and so in terms of the model, we needed some additional CO2 to match the observations. To me, that's very exciting. I mean, the errors, to me, when the models agree, I scratch my head and say, oh, that's boring. What else is there to learn? Okay, so when there's a disagreement, I perk up. So at this stage, and so quoting Charney, all I can say is at this stage of the study, we can claim no more than to have shown the possibility of simultaneous assimilation of observations of meteorology and atmospheric composition, and producing a 4D, if you will, a reanalysis of CO2 in the atmosphere. So with that, we can start the process of cross-checking CO2 sources and sinks at the national level, where not just rely on self-reported statistics. And so the important thing that has been said many times in CO2 inversion studies is that, oh, there's transport error. And I think by building on the meteorological data assimilation, community building on the lessons learned there, then we can actually quantify the transport as well as observational uncertainties in the estimated CO2 sources and sinks. So I'll end with advances. What do we need? Observations. Observations, if you hear me again, it says observations. Okay, I think it would be arrogant of us to think that we know what's going on in the atmosphere. It's non-stationary statistics. Things are changing rapidly. Things are changing in ways that I would not have predicted. So we need expanded observations of the meteorology, of winds, of convective mixing, especially over the ocean. And what we need is greater spatial and temporal coverage of CO2. While I say this is much better than a few sites, 100-ish sites around the world near the surface, the current technology is using reflected sunlight, and so we would greatly appreciate greater coverage at high latitudes, day-night coverage, as well as having vertical profiles. And of course, advances in modeling. And I come back to Charney's my first interaction with him when I was not allowed to do modeling for my thesis. First, you have to understand, okay? So it's really following from Kerry Emanuel's talk, the emphasis is on understanding what is going on, understanding where the failures in the modelings are, which is failure in our understanding and how we proceed. So I'll stop right there. Thank you.
Great. Thank you very much. So we have some time for any questions from the audience.
Fantastic.
Oh, one in the back.
I can't hear you. Can you come up?
So I think the question is, how confident are you in the ocean sink in the simulations?
This is the first experiment, okay? So yes, I work with Taro Takahashi on compiling ocean sink, and there's also data assimilation studies that would assimilate the CO2 observations as well as the biology observations together with the current observations to get CO2 fluxes. Prior to that, the Takahashi maps of CO2 exchange is really extrapolation. Okay, and there was one time at Takahashi's birthday, I said the Southern Ocean has to be not that big a sink, and he says it has to be a big sink, and I said no observations in the winter, and he said he wanted the Southern Ocean to be a big sink because it was his birthday. Okay, so this is a state. I mean, we have to make assumptions when there are no data, okay? So where we really have to go in, it's not just including everything and make everything more complicated, but where are the data to test our understanding?
Great, thank you very much. So we're going to just take a second to sort out, hopefully, a microphone for the audience. But in the meantime, we'll just get our next speaker. Great, so our next speaker is Mark Kane, and the title of his talk is Charney's Influence on Modern Oceanography.
No problem. Okay, I think the technical difficulties are resolved for the moment. Charney was mostly, of course, not an oceanographer, but he was interested in the ocean, and that came from the person I would think of as his primary mentor, Rossby, rather than his thesis advisor. In Oceanography, Charney wrote 5 papers. Actually, altogether, by current standards of many of us, he didn't write a lot of papers. But unlike the papers of many of us, all of them are worth reading. So in Oceanography, there were 5 papers, 2 students, 3 postdocs, and I'll tell you what all of those are, and then we'll go on from there and talk about what it might mean. Oops, okay, maybe it's this way. Work the right way. Okay, so here are the 2 students. I'm one, Joe Pedlowski's the other, who are sort of card-carrying oceanographers. We're both a bit suspect because we don't go to sea, but that's all right. Here are, in an early picture from 35-odd years ago, 2 of the postdocs, Ed Sarachek and George Philander. I'm in the picture too, and some of you can identify the other people in this picture. This picture is just to show that George and I have not changed at all in 35 years. Okay. The other person is George's brother, and that's a long story. Okay, and here's the 3rd postdoc, Stan Spiegel. We'll come to his work in a bit. The person with him is Diana Lees Spiegel, and Diana was Charney's programmer and then became Stan's wife. So Stan not only was a postdoc, but found a wife as part of his MIT experience. That's also true of George, who married Ilda. Okay. We'll come back to some of the people. I've mentioned George a lot then because I'm not going to get into his work, so he gets that too. Okay, so Charney wrote these 5 papers, and the first paper, as I'll discuss in more detail, is a kind of carrying the message of what might be called quasi-geostrophic theory into oceanography. Although it's phrased in this paper in terms of what are called the balance equations. And I'll come back to that a little bit later. The next paper is a beautiful paper that explains, if you will, the Gulf Stream as an inertial boundary layer by making a very clever use of vorticity dynamics. And it followed on work by Stommel and by Monk, in which they closed the ocean circulation using a frictional approximation to have some representation of the western boundary layer. And everybody knew that was not right exactly. And moreover, just what the friction would be was really completely unknown. So this was, if you want, the other extreme, trying to get at what the western boundary current would be is almost in the absence of friction. I suppose the truth is somewhere in between, because the Gulf Stream, as we know, coexists with Gulf Stream rings and other eddies, which make quite a difference in the structure. And the whole structure is not simply a boundary current, but is this quite complex process. I'm not going to talk about that too much because it's, well, I only have so much time, I guess, and I'm going to pursue other things. The two other papers that were written early, one was Charney alone, although really Diana did all the programming for this, and the other with Stan Spiegel, were papers about the equatorial undercurrent. And they were quite important and influential at the time, and certainly had a big impact on me. And the final paper, which I won't talk about at all, came later and is, I think, overall less influential than these earlier papers, but is quite interesting and worth reading. Now, the 1955 paper called The Generation of Ocean Currents by Wind, Charney tells you where he's coming from right away, and that is this paper, and in fact Charney's work on quasi-geostrophic theory were, if you want, a follow-on to the Rossby adjustment problem and the work that Rossby had done on the mutual adjustment of velocity and pressure. And quasi-geostrophic theory was, in essence, a formalization of what Rossby had done more intuitively and allowed you to talk about the balanced motions. Sometime later, people introduced other language like slow manifold. But essentially, what the program was, and it was clearly came out of discussions between Rossby and Charney after Charney finished his thesis on his way to a postdoc in Norway, he stopped in Chicago for what turned out to be about 9 months and met with Rossby. And in essence, out of that and out of another meeting at the Institute for Advanced Study, they sort of formulated the program that led to the first numerical weather prediction. And that was really what motivated, it was this practical problem of trying to predict the weather that was the motivation for what is arguably the most profound theoretical framework we have in atmospheric science, the quasi-geostrophic theory. Okay. So it says later on, it appeared desirable, therefore, to develop a formalism that is specifically applicable to the study of such large-scale balanced motions. And the point is that most of the energy in the winds is long period, and that is going to be generating balanced motions, not shorter timescale inertial motions. Okay. So this was, for oceanography, the introduction, in a way, of quasi-geostrophic thinking. Okay. There had been earlier work which was, I would say, more in the manner of Rossby, more informal invocations of potential vorticity balances. But this was the work that formalized it all. And if you read the paper, it doesn't talk so much about quasi-geostrophy, it talks about balance relations. Because at the time, Charney was quite interested in generalizing QG theory toward a more sort of the next level of complexity, which involved balance, which would allow you, for example, to get the difference between cyclones, the asymmetries between cyclones and anticyclones. Okay. Now, the other thing in this paper, which is profoundly important for oceanography, and as I'll try to get at, was the idea of Ekman pumping. And this, interestingly, came from an earlier Charney and Eliasson paper where they were using the idea of Ekman pumping to formulate a lower frictional boundary condition. And so that paper was the one in the late 40s, and then Charney used the same idea in this paper, and it became something of a mainstay. I mean, the Stommel-Arens theory, for example, uses Ekman pumping as a boundary condition, and it would be almost impossible to try to cite the total body of work that uses this concept as a way of organizing. I mean, one of the things that this slide points out is people made maps of Ekman pumping because, in a sense, this became a fundamental way of understanding what was driving ocean dynamics. Okay, and this paper was the origin of that idea. Now, several of the early follow-ups to these concepts were created by Joe Pedlosky, and I'll start just briefly with what is perhaps my favorite oceanography paper, the Pedlosky 65 paper on the Western intensification, which kind of in the spirit of a lot of what Charney did, it sort of looked at things as an initial value problem. How would the western boundary get to be there? Why would it get to be there? And the way that this was done was, in essence, Rossby waves propagate from east to west, okay? And then when they get to the western boundary, they're going to be reflected as short Rossby waves, which have very low group velocity and essentially are easily pinned to the boundary. And what Joe did in this paper was go through all of the mechanisms, essentially, that had been proposed already. Bottom friction, horizontal friction, which is a stand-in for eddy action, and inertial balances, and showed the way all of these can be melded to the interior which involved Rossby wave propagation. And this was an extension of Charney's paper in the sense that that paper was, like Rossby's, was sort of on an F-plane. It wasn't quasi-geostrophic, it was geostrophic on the slow manifold, and so there was a gap. Going on, this 1968 paper is a paper that points out that if you separate off, if instead of looking at Sverdrup balance, you separate the Ekman layer and you look at that and the Ekman pumping, okay, that even in, let's say, a flow driven by a wind which has no curl, a lot of interesting things go on. You just have to look at what happens in the upper layer and lower layer. The second paper is an attempt to introduce thermodynamics in that. It's a kind of early step toward what later, an unsuccessful attempt toward getting where finally the ventilated thermocline theory gets us. Okay. Now, Sarachek and I wrote a series of papers that also were essentially designed to look at initial value problems and the way, in this case, the equatorial ocean would spin up from rest in these first three papers under different conditions. You'll notice they're numbered 1, 2, 3. And then in a fourth paper, we did essentially responses to periodic forcing. That is not numbered 4 because when George Philander reviewed it in 1980 or whenever, he said that in 2000, and might as well make it 17, I don't remember, when the reader opens Kane and Sarachek part 27, okay, he will immediately close it feeling it's futile if he hasn't read the first 26 parts. So it got a different name. Actually, if I'd understood this paper better at the time, we would have been able to figure out El Nino a little bit more quickly. Okay. Now, I better speed up a bit. Okay, this is a poster that Stommel designed. There had been observational work by Cromwell, and he discovered the equatorial undercurrent in the Pacific. Actually, later people discovered that it had earlier been discovered in the Atlantic. But people came up with theories, and the only one actually that made any sense was Charney's, and he did a model, not this model, but he did a numerical model. He was one of the first people, of course, to use computers seriously in his work. And he did a numerical model which just did things on the equator as a function of z, as a function of the vertical. And then with Stan Spiegel as a postdoc, they did this work that was in the YZ plane, okay? And in one sense, it gives you a picture that looks like the undercurrent and the circulations off the equator that go with it. In another sense, it's kind of not very satisfying. You change the friction from 14 CGS to 17 CGS, and the speed of the undercurrent more than doubles, okay? So clearly you haven't pinned it down very well if it's that sensitive to friction. And in a way, the problem with this, which I think Charney understood, was by not putting in the downstream changes, the changes in X, you ran into, essentially the same water is cycling around and it's speeding up, and it's the vorticity balance that was at the core of the theory was working against you. So he had this other problem. He wanted to do add X to this problem, and this was at the beginning of GATE, and he tried to give this problem to Sarachek, who didn't want to learn how to program. But I already knew how to program, and I didn't want to work on the balance equations, so I became an oceanographer. And my thesis model, which was essentially Charney's design, there was a surface layer, which was like the Ekman layer, and an active layer. There was no temperature in this, except that there was a lower layer which was motionless. So this was a kind of minimal model, if you will, for trying to get at the XY circulation and the undercurrent. And this design we carried over into the models Zibiak and I made for El Nino and the Southern Oscillation. And the key thing there, the key thing we added was thermodynamics. So in this model, the surface layer has temperature, and it has currents that advect temperature, and it has communication with a lower layer that can also change the temperature. I'm just about done. And, but in essence, the idea, in a way in those days, given computer power necessity, was to do a coupled model. And it was, I think, this design was clearly a large part of our ability to succeed. Okay, and we did a simulation, and then we did a prediction. And I want to end with this. Once, toward the end of his life, Charney expressed to me his great disappointment that numerical weather prediction had not progressed any further. Okay, this is circa 1980, let's say. Okay, and if you go back, you can see that why he might have felt that way if you go back and you look at the progress from the 50s. Okay, and what I'm showing here is a plume of many models that the IRI CPC puts out all the time. And I'm showing this in part because our simple model, in competition with all of these GCMs and others, was, for this year, the only one that got it more or less right, okay, starting from March, okay? And that's a bit of luck, in one sense, but it does say that this model, which is now 35 years old or so, is still competitive. And so I suppose at this point I'll ask, why these predictions aren't better than now, and maybe we can get into that a little bit in the panel discussion.
Thanks very much. Probably have time for one quick question if there are any questions from the audience. If not, I'll hand over to Jagadish Shukla, who'll be heading up the panel discussion.
Slide right away. Yeah, keep it this one, and then change. No, go to like here. Then.
So I'm wondering what the best way is to.
Yeah. Okay. Good afternoon. I think now many of you are going to participate actually in the rest of the discussion. There's going to be a panel discussion, and in a few minutes I'm going to invite the panelists, the three speakers, Dr. Halem or Stevens. But before we start that, I just wanted to mention a few things about Charney and about the last century. Charney was born on 1st January 1917, and I think that 20th century was probably one of the greatest centuries, of course. What a century for weather and climate, and I'm sure there will be very few objections if we said that Charney actually played a major role in the development of our field in this. And we have heard a lot about his science and so on. I just want to tell a little bit about his humanity, a small story that how actually I met Charney. Imagine 1968, I'm a 23-year-old man from India, just sent by accident to talk about a paper I had worked with Dr. Gambo of Japan, criticizing work by Charney, where he had written a paper that there's no vertical coupling in the tropics. And I had no idea who Charney is. I just run the model for Gambo, but he said, you present it. And so I asked somebody, who's Charney? And they said, that guy's name is Charney. And then I started noticing that these Japanese people were taking pictures. Every time he will wake up, stand up and ask a question. I got so nervous by the time my paper came, and I was speaking so fast that Bert Boleyn came and said, you are speaking too fast, people are not understanding. Well, I was so nervous. I just had to somehow end up by criticizing his work, because my point was there is vertical coupling in the tropics, because I had changed the Richardson number and redid the experiment. And is there any questions? And nobody raised any hands. And I was feeling so relieved. I said, okay, I'm done. I'll go home. And then Charney raises his hand. He says, 4 questions. I have 4 questions. And now I don't know where from I got that nervous energy to go back and forth with Charney for the next 2-3 minutes. Anyway, his 4th question was, your result proves that I'm right. I said, yes, sir. Okay. And then I thought, I'm done. And then there was a coffee break. And that what happened next is really tells about his humanity. I was just sitting there arranging my thing. He came to my table where I was sitting. He says, I have written another paper, a further note on motion in tropics. And it shows, and I was just so nervous, because by that time I knew this is a very famous guy. And he says, I want to give you the other paper. Walk with me to the hotel. The reason I want to tell you this story is because that scene I cannot forget for the rest of my life. I'm walking from the lecture hall to his hotel, behind him, Charney, me, and behind me, 12 members of the U.S. Golf Committee who really wanted his attention, but they couldn't get hold of him because he was the chairman of the Golf Committee. Of course, I decided, okay, I'm going to be a student, and I wrote to him, I want to come and study at MIT, which he never replied, of course, as most of you professors do. But Phillips did write me a letter saying that, okay, you can apply. So I really think that, we all know about his work with the Vietnam War. We know what an activist he was. But he was not only a great scientist, he was really a great human being. And in fact, I had decided to give a brief introduction of his contributions. Can you just go to the next slide? And then I realized Kerry has already done this. So that's how I thought, okay, I'll use my 2 minutes to give my story. So you have already gone through his work. I'm not going to take his work. I'll only mention that it's amazing, the one person who knew how to use models for asking good questions. He did it for estimating predictability, for Gulf weather experiment. He asked for estimating impact of biological feedback. He did it for CO2, collect all the models. And I think he created that, give that respect to the modeling field. I really wanted to ask Ed Sarachek, who really came, who couldn't come, and he asked, do you have any comment to say? And he just told me 2 sentences. He said, Jule Charney was a man who enjoyed thought. He basically said that whenever he talked to him, and if you ask him a deep and profound question, you could see his face will relax, and then he will light up as he's thinking. And Charney was a great thinker, but a terrible classroom lecturer. I think it's very, very difficult to follow his lectures, and I'll tell you. So I think that I'm going to contributions on science, but also the second contributions that scientists make is produce PhD students. But these are all the PhD students of Charney. I'm sorry to be self-serving, but you can just see the incestuous nature of this session. Most of the speakers I think that, and I'm just going to put now on the screen the 3 questions that we'll be discussing, and you want your input. And I have the names of the panelists here. Mark Kane, Kerry, Emanuel, Inez, Fung, you have already heard. They are so famous, I don't need to introduce them. Well, the second 2 panelists are also very famous, but since you haven't heard, I want to, Milt Halem is the one who really brought me and Mark Kane and Inez all together with Jule Charney. He was at GIS, New York, and then he moved to Goddard, and many of us moved with him, and he worked with Charney on the satellite problem, assimilation that Inez already told. And Bourne Stevens is the director of the Max Planck Institute for Meteorology. So this is the members of the panel. These are the questions. I would like to organize this panel discussion in the following way. I would like the panelists to make some very brief comments, very brief, especially so that, and then we'll open up to the audience. And we'll like you to ask questions and make your comments. And if there are questions you want to ask the panel, or you want to make suggestions about what the future of meteorology is. So with that, I would like to request the panelists to come, please, and take your seats here on the podium. All of you, please. Bourne Stevens, Mark Kane, Inez Fung, Kerry Emanuel, and Milt Halem. I can use this chair. To come forward, yes. Yes. So as you can see, everyone who spoke and who has been identified till now had some deep, long-term association with Jule Charney. We're really grateful to Bourne Stevens, who actually agreed to be part of this panel. And I'm actually going to ask Bourne Stevens first to go, if you can make some click. Yes, yes. And by the way, Bourne Stevens is the winner of the Charney Medal this year. And you can turn on your... I think they're on. Oh, they're on already? Okay.
Yeah, you can hear me? Okay, I will try to keep it brief because maybe we can have a discussion in such a large room. But from my point of view, the emerging question is a very, very old question, but it's one that the field is poised to answer. And that's really how the diabatic processes, clouds, convection, radiative transfer, couple to the largely adiabatic motions of the atmosphere. And I think it's an exciting and important and emergent question because finally we're poised as a field to really begin simulating the atmosphere in 3 dimensions. Now, that might come as a surprise to you, but I think most people don't really appreciate the extent to which almost everything we know about the atmosphere in terms of simulations is based on fairly crude 2-dimensional models stacked on top of each other, shallow water equations stacked on top of each other, which are coupled in the vertical through, well, that's the crude part, the parameterizations of heat and energy transport. So if you stop for a while and think of a general circulation model like we use in CMIP, it's really a beast of the mid-latitudes and doesn't represent physically the modes of energy transport in the vertical, especially in the tropics. And now we're developing the tools that allow us to look into that third dimension. And at the same time, we're looking into the ocean in ways where we can resolve the mesoscale and the submesoscale in the ocean. So it's a very exciting time to really ask how diabatic processes couple to adiabatic processes in the atmosphere. And that I would put as the emergent question. On the second one, what should be the focus of research for advancing our understanding of the predictability of the coupled ocean-land atmosphere system? And on this question, I wanted to object because there was this phrase, in providing I can't even say that word, societally beneficial predictions. And I wanted to object to that idea of providing societally beneficial predictions. I wanted to object on 2 grounds. The first ground was I can't say it very well. But the second ground I wanted to object to was that somehow we've sort of fallen into this misconception that the job of scientists is to be useful. I kind of think of plumbers and cooks and teachers and librarians and bus drivers as people who are useful. I think the chief job of a scientist is to be novel. And by being novel, we've proven time and time again that we're useful. So I think what scientists should really worry about is how to do new things, not beneficial things, and trust the fact that in doing new things, we will be useful. And if we don't have the confidence to say that we do new things that end up being useful, then who else is going to say that? So I would go around that question and say we should wonder about what are the new things we can do. And I would trust in the fact that they'll be useful. And as for preparing the next generation of scientists, I would just go on from that and say we should attract them to the opportunities to do new things. And here the opportunities are these new tools that we're developing that allow us to look at the atmosphere and the richness of all 3 of its dimensions, and in the ocean in the richness of all of the fluid dynamics that we can now solve in terms of the power of computing and a whole revolution in observations. So I'll stop there. Thank you.
Okay, thank you. I don't want to get into a discussion right now, let me all, but you heard Mark Kane's presentation. Charney was motivated by making societally useful weather predictions. Later on, he also we'll come to that question of, can I request now to Milt Halem to make some brief remarks?
I'm sitting next to Inez, and she put up a slide. I think she had the incorrect date. It was 1969. 69. That the paper was published.
Okay.
Yes.
You're the author.
Yes, yes.
Well, there was somebody that was working on that paper with me, doing a lot of the calculation. He's sitting on the other side of you, and I guess he will. But let me. But
let's go on. Yeah, let's go on.
But that's not the point.
Go ahead to your comments.
The title of that paper was on the use of incomplete historical data to infer the current state of the atmosphere. And what he left out when he said on the use was on the use of numerical weather predictions coupled with long historical data to infer the present state of the atmosphere. And he believed that that was the tool that was necessary to really address all the list of fundamental questions that Shukla listed in his 10 or so contributions. He also believed, he believed in the output of numerical models, and he would question them. He would do more experiments, and it was a tool at that time that drove him. I remember once he had some economist friends who were doing some nonlinear calculations of the in economics. And he also wanted to use numerical models there to try to explain economics. And this was back in the early 70s. So I think the fundamental thing that Charney brought to our understanding of climate dynamics research is the need to continue to develop and harness the power of computational capabilities to answer such a fundamental question. Now, when you go to the next question that Shukla posed, what should be the focus of research for our understanding of the predictability of climate, decoupled climate, ocean, land, atmosphere system? The answer that he would give, of course, is that we need to couple into our models with sufficient resolution the multiple states of the climate. And we have some of that work going on today in several places, in Switzerland and here in the U.S. at both with the DOE and NCAR. And so people are still looking to harness our new computing technology to really address that problem. The third question on the board, how do we prepare the next generation, is sort of self-fulfilling. Our students today have, because of the availability of cloud computing systems, students today have access to computing capability well beyond what anything we had in the past. And that's how I believe what we have to do to further this effort is to continue to make available to the next generation of potential scientists the availability of such tools to really address such questions.
Okay, thank you. Thank you, Milt. Now, the next three panelists had spoken already, but would you make some brief remarks on some of these futuristic, because I think in the panel discussion, we want to look for the future now, not going back. Inez, you want to make some comments?
I think we all grew up with Navier-Stokes, and so the numerical weather forecasting is the left-hand side of the equation, except for the pressure term. And then with the climate, we add the radiative forcing, all the forcing, and now I think I'm moving more to the right-hand side of the equation to say that we have to include what is changing the forcing for the radiative, what changes in the atmospheric composition and the land cover that would change the radiative forcing. To look at the problem in total is very important. And so to me, the most important thing you hear me again and again is that we need observations. That the way that we learn instability is here is a basic state, and then you do e to the ikx minus omega t, and you find the waves and the instabilities. But the basic state is changing. This basic state is changing, the background state is changing in unpredicted ways. And so how the storms and how everything will change on top of that, I think requires new insight, and the issue of multiple equilibria obviously comes up. Before I go to the third one, I want, when we were students, we worked nights and we worked weekends. And Charney subscribed to Gourmet magazine and the New Yorker, and you try to read those and make sure and hope that he didn't find out that you had read them. But one thing that stuck with me now, much later, is, and I encourage everyone to read Julia Child's recipe on hollandaise sauce. Because first she says, you can make it with machines, but you have to do it by hand once in your life. Okay, so that you understand how things mix together. But much more important in that recipe is that it says, if your sauce doesn't mix, this is because you have not done this, and this is how you remedy it, okay? And so when I go to the third part, I say, yes, you will have all the tools, but it is very important to fail, to make mistakes, and to not be afraid to make mistakes so that you can learn from them. And this is what experience is called. And so it is very dangerous to rely on a big model, and then you come to me and says, the model says this. And I said, who is the model? Who coded the model? There's nothing that says the model says this. Okay, so it's a basic going back to the fundamentals and to try different things and learn from your mistakes. And I think that's the most important thing, the most important lesson I learned from Charney.
Okay, thank you, Inez. Mark, do you want to add something about the future?
I guess I'll talk about the ocean because nobody else will. Mostly recently I'd felt like if you're going to work in oceanography that you should be interested in biology or you should be interested in climate, because it didn't seem like the ocean problems of a classical sort were that interesting. But I've changed my mind recently because there's a slew of observations, particularly from the Atlantic, and we have new observational tools in the Argo floats. And the Atlantic work in particular has completely overturned the classical picture of how the ocean works. So that's really exciting because it's time to rebuild. Some new paradigms are needed. The old ones, if you talk to most oceanographers, they'll give you the same stuff, but it's already clearly out of date. And for example, the overturning circulation simply doesn't work the way it was envisioned by, Stommel-Aaron's model. It doesn't, on the short time scales we can observe, doesn't work the way we use it in discussing paleoclimate. And so I think, this is an exciting thing to do. Probably a more urgent thing to do would be to understand a little bit more about how glaciers melt, and in particular for Antarctica, what the role is of the ocean in essentially eroding the seaward edge of glaciers, which seems to now allow them to flow rapidly in the sea. This would seem to be an important question especially for those of us who live in low-lying coastal areas, which on this planet is most of us.
Okay, thank you, Mark. Kerry, do you want to make some comments about the future?
Let me just begin very quickly by endorsing Bjorn Stevens' view that the interaction among water vapor clouds and radiation is one of the most exciting and important things going on in the field right now. I really feel that way. And with that, I'm going to jump right to number 3, the third point. As an educator, I would feel myself successful primarily if I taught my students something that Jule taught me, which is the sheer joy of understanding something. And Jule provided a framework that we all use for understanding very important phenomena going on in the atmospheres and oceans, things like baroclinic waves, turbulence, boundary currents. What was lacking in my education, and I think in the education of many of those up here and probably amongst you, is that we taught the equations of radiative transfer without teaching the equivalent conceptual understanding that went with it. And I had to try to do it myself, and I don't feel I'm there yet. And we're not doing that. And I think we really, as educators, addressing number 3, we really have to try to give students a feeling for radiation, not just the equations, and the joy of making discoveries of the kind that I tried to describe in my talk. I think there's a lot of future there.
Okay, thank you very much. Before I actually invite the two organizers to make some comments, I just wanted to add a comment. Mark said that Jule was not very happy about the progress in NWP at that time. Well, he will not be very happy even probably today. But I think that the reason is very clearly what Bourne and Kerry had said. Potential velocity dynamics has taken us as far as we can go in the weather prediction. And I really think that we really have to go through the next step of being able to take convection and moist processes into full consideration. Because I think we have squeezed as much as we can by increasing resolution with the weather prediction. So I think that both suggestions are absolutely right on the button. That is a big challenge for the future. I do want to ask both Natalie and Paul, but before I wanted to ask Paul, because we have heard about ocean and atmosphere. We didn't hear much about land. I just wanted you to know that COLA, the Center for Ocean and Land Atmosphere Studies that Jim Kinter and I have been involved with for many, many years, the origin of that word L really goes back to Jule Charney. He actually wrote a paper on the albedo effect in the biogeophysical feedback, and he gave that paper to a draft to read. And I went to Yale Mintz, and I said, Yale, this paper is so badly written. And Yale read it, and he says, this paper is written the way he gives lecture in the class. And so we actually went to him, and I said, look, you are talking about albedo, but most of the results say swall wetness. It is actually the swall wetness really is the one which produced most of the effect. And that paper was really the motivation for Yale Mintz and I to do this crazy experiment where the whole world was changed into a parking lot or a slump to be able to get. So I really like Paul to make some comments about what do you think the land-atmosphere interaction, land-climate interaction, where is it going to go?
All right, well, Shukla's completely caught me off guard here, but I'll give my elevator speech. Yes, I think that the land research is kind of where ocean was at the sort of the Keynes-Ziebiak model phase, because we're maybe running 15 to 20 years behind, but we're right, I think, at the cusp of that great advance, partly because observations are coming online and partly because we can confront models now with them and with theory, that we can understand much better now how the land surface contributes to predictability in the climate system and start to take advantage of it, finally harvest that. But the one thing that I got really excited at, of everything I've heard so far, is what Kerry said about coupling the conceptual aspect along with the technical mathematical aspect, which is something that's, it's a cornerstone of how I try to teach. And because there are people who are mathematical and there are people who are conceptual and there are a few who are both. And I think it's kind of up to any scientist to work on the weaker side of their brain in that aspect to bring the two together, because that's really where the full understanding comes from.
Thank you. Thank you, Paul. And again, Natalie, before I open it up, first of all, thank you for organizing, but you are the second generation Charney kind of connection. Philander was his student, well, one of his students. You have worked with Philander. Please give us your perspective on what are the future questions that we should be all thinking about.
Well, I sort of actually wanted to rather throw the question back, because we heard the panelists mention sort of the various directions in which the future generation should be going in. And in a way, channeling George, because he's not here, I would want to ask the question, do you see a room for paleoclimate in all of this? I mean,
of course. I don't even understand why you asked the question. Of
well,
course.
Well,
I mean,
it didn't come up, right? It didn't come up.
Well, because of the time.
Because Shukla was on your back.
Okay. I mean, I would say that, I think the best problem in climate, if you need a best problem, and it's good to have a good problem to work on, is probably to understand the Younger Dryas, where there's this, 2/3 of the way back to an ice age in 10 years. How is that possible? We don't have an idea of how that would happen, and since we don't have an idea of how that would happen, I feel all of our confidence in, or whatever confidence we have in future projections is suspect. It's true it was a different world with more ice, but nonetheless it was the same climate physics, and if we don't know how that happens, how do we know something like it won't happen next year or 10 years from now?
Well, that's thank you from our question was whether there is a future for paleoclimate, and Mark is saying it is the best problem. So that's wonderful. That's a switch. I really would like to open it up for questions by the audience. I'm sorry we could not get the microphones to be into the audience, but if you speak loud enough, I'll repeat the question if you're nearby. So I would really like to open up to the audience your questions to the panelists, if you have any, your comments about what are the challenges for the future, and what are the questions that you would like to see to be addressed to advance the science. By the way, the word climate dynamics, I just forgot to mention to you, the word climate dynamics was the title of Charney's proposal to NSF 40 years ago. That's sort of, that's the first time that I came across that word. Okay, so any questions from the audience? Because yes, Kevin, you can talk loudly, I think you can, right? Okay.
So Kevin, I would just amplify that. I was maybe using code words to say the same thing.
Can you just repeat the question just for...
So Kevin was complaining that we weren't speaking enough about moist dynamics and problems, for instance, with precipitation. And the thing that occupies me a lot in that regard is that the world's going to get warmer. We know it's going to get warmer. So when we think about a 2-degree warmer world, what's the tropics going to look like in a 2-degree warmer world? I don't think we have a clue. Our whole view into the future of the world is through these models that can't even produce the diurnal cycle of precipitation in the tropics. I mean, think about that for a second. It just struck me. We say this a lot. It almost becomes glib. Models can't produce a diurnal cycle. You can kind of work on them like ECMWF did and get better answers. But is there anything that's more well observed? Is there anything that's been known for longer? Is there anything that's more strongly forced than the diurnal cycle of convection over land in the tropics? And we have models which are our window into the future that can't do that problem right. I just find that fascinating. I mean, the potential for the tropics to do funny things in the future is huge. And the sooner we get an understanding of those problems, the better prepared we'll be for this warm world we're heading into. So I agree completely.
Thank you. Kerry, do you want to comment on this?
Just very quickly, I think, Kevin, to push back a little bit, there has been, in my view, really a lot of progress in moist dynamics. It's a harder problem, mostly because of the difficulty of making observations. But I think we've seen reasonable progress, exciting developments conceptually, like the weak temperature gradient approximation, Brotherton and Sobel, made a lot of progress in conceptual understanding. I think there are many areas where we've done field experiments and emerged with a much better understanding. Are we there yet? No. But it's not as though nothing's happening there.
Natalie, I almost thought your hand was going up.
Yeah.
Yes, go ahead.
I just want to maybe throw it out there that maybe we don't have a clue for the future, but I would argue that in looking at past paleoclimates, we do have analogs for a 2-degree world. And at least in terms of large-scale structural changes in the tropics in a warmer world, we have a clue from the large-scale sea surface temperature reconstructions what we may expect. Obviously, there's uncertainty around that. And we should be challenging our models to at least try and recreate that. It's just
yeah. And if Philander was here, he will completely agree with you. Okay, any questions? Yes, sir. So the question is about planetary modeling. They're just going beyond planet Earth about this. And anybody from the panel would like to respond to that?
Yeah, there's quite a bit of work going on, applying what we have learned about the Earth, and I'm going back many decades to Conway Leovy's study of the Martian atmosphere, and now to the other planets. And one thing is to do the fluid dynamics to explain the features on other planets as well as exoplanets. But I think, from my perspective, knowing the forcing would be very important, and knowing the composition, which is something that we have not yet been able to do. I'm sure we'll be doing it soon, but not yet. So there's a bit of freedom in science fiction so far in our modeling.
I think this is already on. I think your question is very important. I think especially the exoplanets. We have an exoplanetary scientist or two in my group, and it's absolutely fabulous what we're learning and discovering in the realm of dynamics and thermodynamics. And Ray Pierre Humbert has a spectacular paper on the dynamics of pure water vapor atmospheres, and it's absolutely beautiful work. So it's a very, very important and exciting frontier.
Actually, I want to ask a question to the panel members. Rather than criticizing the models, let us see what Charney did. He actually took models which are pretty lousy, but he decided that they're still valid tools for asking questions. When he estimated the predictability of weather while he was launching the global weather experiment, he took models which were just, imagine, in 64, 65. When he did the CO2 problem in 1979, those models were just nowhere near the kind of models we have. So, and so on and so forth. It's the same thing he did about the albedo. My question is that, can you make some suggestion about what to do about going through this next step of models, which be able to answer the kind of questions that we are? Does anybody have some suggestions about how do we go forward in building the kind of models that you want to have?
I mean, we can simulate the world at 5 kilometers now. The Japanese have been running climate experiments at 11 kilometers. There's a whole new generation of models which are resolving the overturning of the atmosphere. And I think putting our effort into bringing these into focus has two advantages. It gives us a new glimpse at the world in a way that we haven't seen it before. And the beauty about representing the world with these very high-resolution models isn't that they're suddenly true. I mean, they have more physics in them. But the nice part is you begin to simulate the world in the same way that you observe it. And so you naturally move towards data. And I think one of the problems that at least I perceive and in the prediction problem is that so much of the predictability work on longer timescales moves you away from data. And I think science is always, and that's why the paleo problem also is a great problem, because the paleo, sometimes I wonder, Charney was brilliant on the paleo actually, because 1979, the Charney report, there wasn't even a murmur of ice cores in that report. So I always was fascinated how, yeah, I know, but it shows you how it wasn't a criticism of them. The Barron people were beginning to look at some of the ice core, but it shows you how what a revolution can happen. Suddenly, with the ice core work, we had a whole new view into the climate system. And so we shouldn't rule out the ability to get more and more information about the past. But everything we should do, we should take those paths that lead us to data. And one of the things that make me so excited about high-resolution modeling is it brings you towards data in a way that parameterized models don't.
Well, I will push back a little bit. My question was beyond resolution. I have seen enough high-resolution model simulations, so many of them, that I know that's not the actual complete final answer. We have so many simulations with 3 kilometer, 5 kilometer, but the errors in those simulations are much larger than anything you can expect, which for solution is resolution. So I wanted to bring back to what kind of mechanisms are there to bring the moisture and convection and moist physics with this resolution. What kind of institutional arrangements we should try to see that can happen? Increasing resolution is simple, and people can do it, but that is not solving the problem.
I'm not sure if I understood you, but things like the sea breeze?
No, if you look at the systematic error, say of ITCZ, the error is much larger than the resolution, whether it is a 5-kilometer model or 200-kilometer model. My question was, how do we combine the high-resolution modeling, which is quite easy, with the considerations of moist convection, diabatic heating treatments that one we have been talking about? What's the challenge? What is the barrier? Why we're not able to make that breakthrough?
I asked Charney this question, how do you know that you've got the right answer? And he said you take away everything else and see if you following what Kerry said, you simplify, you take in the model, you take away everything else, and if you have got the minimal mechanism, then you know those are the at least that is a viable explanation. That what we've been doing is add and add and add and add two models. We've been less successful in subtracting from these complex models to understand what are the fundamental mechanisms that are operating to give us the phenomena that we simulate.
Yeah. Well, I mean, this is an age of anybody from the audience wants to comment on this sort of competition we have between complexity and resolution and how much a number of ensembles doing paleo and we just have we're in a 4-dimensional space. How do we go forward to be able to create the kind of tools that we can answer this question? Anybody wants to comment from the audience?
Disagree? Anyone wants to disagree?
Anybody wants to?
This is a conversation.
I'm sure Dr. Kinter has something to say. No? Okay, all right.
I would argue that we haven't seen a couple of climate models that are actually doing what Warren is saying we should be doing, and that is we are not in the current models getting the overturning circulation of the atmosphere right. We're still parameterizing the noise dynamics, the noise physics. Until we get to the point where we're not actually parameterizing those things, we're actually resolving the direct numerical simulation, we haven't actually gotten to the threshold that everybody's been talking about. So I would say that you're right, that the systematic errors are still there. We haven't made a lot of progress on that with resolution. But I would argue that we've just been in a plateau of resolution from 100 kilometers down to 1 kilometer. We haven't gotten to where we need to be.
Oh, I think that's not a disagreement. What I was saying is that resolution alone is not really the solution. There is a lot more than the resolution.
I'm saying we have to get rid of the parameterization.
Okay. So there is a hand there in the back. Do you mind just coming a little bit further because I want to be able to repeat the question. Yes, please. Very good. So the question is that what do you think is the future of stochastic forcing in the parameterization system, in the models? Anybody wants to comment on that?
I'll have a crack at that and maybe the previous discussion too. Ian James, one of my favorite statements is Ian James' quotation that comprehensive complexity is an admission of failure. And maybe he was going a little bit far, but we are never going to get to the point that Jim wants to get to of not parameterizing something. And let me tell you, what we will always parameterize is cloud physics. I don't think we're going to get down to molecular scale global computing anytime soon. And this is where just computing isn't necessarily going to solve problems, maybe some. But, I've been arguing until I'm blue in the face and not very successfully for decades that the water vapor content in the atmosphere is at least partially controlled by cloud physics. It seems like a no-brainer to me. But the cloud physics community does their thing, and the climate modelers do their thing, and Bjorn is one of the very few people who bridge that. And there are a few more coming along, but until we understand how cloud physics actually controls water vapor, or all the things that control water vapor, you know, we can keep increasing resolution, and we can do away with convective parameterizations, and that may solve some problems indeed. But what are we going to do about that? And that's where this whole way we tackle complexity has to involve conceptual understanding and the teaching of that. I don't see how we can get around that.
But yeah, maybe if I would chime in, that's to me that's also the beauty of bridging this overturning, because right now when we're faced with the microphysics problems in GCM, you're trying to couple the microphysics to a convective parameterization, and you just have none of the dynamics, which is the source term. So it seems like the sooner we make this leap to this new generation of models, the sooner we'll be working on those problems that we're going to have to solve, because there's for sure things that we won't be able to resolve away on a global scale. And the question is, what are those things, and are we working on them? So sometimes I feel like we're spending too much time working on problems of the last decades and not making this leap. So microphysics will be one, but I like to think we can solve that problem if we know the forcing. I mean, if we have the updraft velocities, if we can observe the microphysics. So this is a fascinating area of how dynamics couples to microphysics. But like you said, actually, we're not even working on it. But I think we're not working on it because we lived in a world of distorted macrophysics, which didn't allow you to communicate with the microphysics.
Well, do you mind, you just made a very interesting comment, the new generation of models. Can you just expand on that? What is your vision of new generation of models?
Well, the way I like to think about it when I teach climate to people who don't think about climate very much is that there's sort of two things the climate system has to do. It has to move heat from the equator to the poles, and it has to move heat from the surface to the atmosphere. And Smagorinsky realized that rather than parameterizing Berkeley inequalities, he would try to solve them, and that gave rise to general circulation models, which are pretty good at resolving the instabilities that transport heat from the equator to the pole. But to resolve the vertical heat transport in the atmosphere, you need a grid scale, which is small compared to the depth of the troposphere. And then you begin being able, in a distorted way, to represent that vertical overturning. And computationally, we can do that. So there's this huge desert, I would say, of scales between what we started with in the 60s and 70s when we had GCMs running at 400 kilometers, all the way down to, say, 5 kilometers. Not a lot happens in terms of these really important modes of heat transport. But once we break into this kilometer scale, which we can computationally now, we get this second mode, this very important mode. I don't know the story in the ocean, but it seems to me some people like to think of the mesoscale in the ocean as sort of the weather of the mixed layer. And this ability, at least my vision, of being able to do the fluid dynamics of a vertically overturning atmosphere and the fluid dynamics of ocean mixed layers, it will open up a whole new way of seeing the world, and we should spend all of our energy trying to get there as quickly as possible.
Very good. So the kilometer scale modeling is just beginning to sort of develop. Still, it is quite limited by this. Right? Yeah.
We've done it for a while.
Exactly, yeah. But on the global scale, it is still a big challenge. Yes. Any other questions from the audience? Because the question about the education part, we really didn't really touch on that. Although, Kerry, I mean, we all mentioned that we should have. There are 50 universities in this country at least, right, which are teaching climate dynamics. Probably more than 50. What any panel member would like to recommend, how do we sort of structure our educational program to prepare this next generation of climate scientists?
Shukla, I think I'll speak for myself, that the field changes every decade or so, that the emphasis changes. So for the students, it is very important to be equipped, not to solve the problem of today, but equipped with the tools to study on your own and ask questions on your own to study new things as new questions emerge, as new data come in, and new things happen. And so the most important thing to me is not so much what problem are you going to solve for your PhD thesis, but are you equipped to ask new questions? And are you equipped with the whole breadth of earth science to have the basis to build as new things come along?
Anybody else has any comment on the education? Because there's a real challenge. When you, Inez, and I, and Mark were graduate students at MIT, atmospheric dynamics was the most important thing. As Mark said, there were very few oceanography students, Jule Charney, although there are other oceanography professors. Now, when we teach climate dynamics, we have to compete. Okay, how much atmospheric dynamics? How much ocean dynamics? How much land we need to take part into it? And then some visitor comes and says, oh, you're not doing biogeochemical cycles at all in your department. They say, yes, we are not. And then another person comes and says, you're not doing stratosphere, and what about paleoclimate? The question is that as complexity of the question is increasing, how does the educational system adapt to it? Because I have kind of two models.
You have to teach them to learn on their own. That's the whole point. They have to. My most important thing for my students is to teach them to live without me. That's the whole thing. We overlap for 4 or 5 years, and then they've got 40 years ahead of them. So I'm not going to be around, so they have to live without me. So we have to start early.
I have to first teach my students to live with me, and then live without me.
I think this is a point where Charney's influence on my teaching is something I think about a lot and wonder, because in essence, he did two things. As Kerry mentioned, okay, the sheer joy of doing science was what he gave us most. And also, although, I won't go through the whole character analysis, but he really just enjoyed doing science, and when somebody else's idea excited him, okay, he really could get excited about it. It wasn't, wasn't all personal. When he taught his class, it was impossible, basically. And I would try to read the notes in order to be able to ask him questions for an hour and a half twice a week, so that he wouldn't lecture, and instead we could get to watch his mind work, okay? And apparently he got this from Rossby, who was pretty much the same. So, I don't know, but it surely prepares you to learn on your own, as Inez was saying. And it was quite the, they were probably the least beautiful lectures you can imagine, but I learned the most from them.
Yeah. Well,
and I'll tell the anecdote that I remember one time, I can still see him with his coffee cup and scratching his head like this. And he came in Monday and he said, I just realized the homework I gave you last week is not doable. And you say, thank you very much. We all worked together over the weekend and we figured it out. But that was very important to me, that he led us, whether deliberately or not, he led us, into pitfalls, and we learned to dig ourselves out, and that's a very important lesson for me, and it was always like that. And I used to joke that when I was undergraduate with Greenspan, when Greenspan had errors on the board, I had to march up to the front of the room, and Greenspan would reach into his pocket and give me a quarter. So I used to joke with Charney that I would collect a lot of money from him because there were so many mistakes. He changes coordinate system in the middle of the derivation, he changes symbols, he changes everything. But what you learn is not the technical aspects, but the thinking part. And I think that's very important.
Yeah. Well, since we're talking about anecdotes of Charney as a teacher, let me just tell you, when I went back to India, people asked me, how did Charney teach you meteorology? And my answer was, he taught me meteorology the same way my father taught me swimming. And I can tell you how my father taught me swimming. Next to my village, there was a big pond with a lot of water. In the monsoon season, it will get filled up. My father took me one day and just threw me into the pond. And he was hoping I'll somehow swim and come and get to him. So he was not going to let. So he never actually told us any answers. He just told us the question, and then you have to figure it out. That sort of.
I wanted to add one other kind of thing. Once people at MIT, where I was at the time, got interested in El Nino after the 77, 78 season. There was a blocking event, and we got this enormous snowstorm in Boston. And, and then it was sort of understood that this had something to do with the temperature pattern in the Pacific, probably. And that was related to El Nino, probably.
What year was you talking about?
What year was that?
Yeah. Because I can tell you,
The
1970.
snowstorm.
Oh, snowstorm. That was much later. Yeah.
That made Dukakis a presidential candidate. And anyway, so I said to Charney, somebody should really figure out how this El Nino thing works. And he said to me, well, why don't you do it? And I felt a little stupid at the time, but it was an extremely important thing. I mean, it sort of was like he thought this was a problem I could do. Maybe, I'm not sure I would have figured out that it was a problem that I could do if he hadn't said that. And, that's the other thing. I mean, people have to be taught a certain level of, if you want, fearlessness and self-confidence to just go ahead and try these things. And of course, most of the time, whatever we do, it doesn't work. Okay, and you have to get through that.
Okay. By the way, he brought El Nino. I should tell you that 1972, we were all graduate students, and big El Nino was raging in the Pacific. Nobody in this department, which has the world's greatest meteorologists and oceanographers, had any clue what was going on. I never heard the word El Nino. And only when I went to India, then I found out there was a big drought. And again, no relationship. We had no idea. So young people, you have just imagined where you are today. Every day you get your picture. It just took several years before we did. By the way, I have just a few minutes, and I really wanted to ask Milt Halem to make a comment on computational technology, and what role do you think this is going to play into the addressing these questions? Just for 1 or 2 minutes, Milt.
I'd really like to point out a different aspect which hasn't been really emphasized about Charney. What you see here is the seeds that he planted at various places, that not only did he bring students to this level of enabling them to attack some of the most challenging problems or questions, but he also wanted to make sure that when they graduated, they were put in a position where they could really take advantage of that. And so I can tell you that Shukla would not have been at Goddard Space Flight Center had it not been for Charney saying you should go there rather than to GFDL. Yeah. I haven't figured out yet why he pushed that kind of thing, but for some reason he felt that that's where he would have a greater chance to blossom. And the same is true with a number of others that came to Goddard. I don't know what brought Inez for her first postdoc.
NRC.
Yes, but you could have...
In New York, and then you moved to Washington.
Well, so he had this this affinity, not just with New York, but with UCLA. He was very tight with... UCLA. I know he went to UCLA. Of course I know that. And, but still, he was very close to Arakawa, and not so close with Yale Mintz, and he did want his people to go to the right institution. So I guess you could also say...
That's absolutely, I think he left his imprint. Well, I really would like to, first of all, take this opportunity to thank the two organizers, Paul Dermeyer and Natalie Bowles, for really organizing this session. It was their work they did. Yes. And I would really like all of you to thank the panelists for really taking sort of questions and taking part in this panel discussion. Thank you very much, guys. And thank you all very much.